Okay, so hello everyone. In this video, we will cover multiple topics and all the topics are very important topics. First, we will see round robin scheduling, then priority scheduling, then process scheduling with IO operations, and at last we will discuss multi-level queue scheduling. All these topics are very important, and you can say it can come in your competitive exams, university level exams, or UGC NET or GATE level exams. So let's start with round robin CPU scheduling. So let's solve a question on round robin CPU scheduling. So in this question we have 4 processes with their arrival time and burst time given. The key criteria of round robin scheduling is the time quantum. First, let me explain what time quantum means. When processes are in the ready queue, the ready queue lies in the RAM. We select a process and take it to the running queue, which is in the CPU. Like we select a process and give it to the CPU to execute. In non-preemptive scheduling, when we give a process to the running state, it gets executed completely. But in round robin, the CPU uses time quantum. Time quantum means, let's say time quantum is 2, then CPU will run process P1 for up to 2 time units. The CPU doesn't care about the burst time. It will just run it up to 2 time units. After 2 time units, that process goes back to ready queue, and then we will bring different process to running state and run that process also up to 2 time quantum queue. In all the previous examples, we have seen that we were maintaining a Gantt chart, but now in this we will maintain a ready queue chart and running queue charts. So if there is still burst time left, we take it back to the ready queue. If a process has a burst time of only 2, then it will get completed in 2 time quantum. The ready queues sequence is the most important thing here. How processes are coming in the ready queue and how they are getting preempted and going back to ready queue again. In round robin, you should maintain 2 queues because it's very important. It will be clear why you have to make a separate ready queue. Let's solve this question. The mode is preemptive and round robin is always preemptive because after every given time quantum, CPU will switch between processes. Okay, this is called context switching. At time 0, which process is ready? At 0, only one process is ready, P1. Then we place it in the ready queue first. If there are other processes ready, place them in the ready queue according to the arrival time. Now extract P1 from here and place in the running queue. We run P1 from 0 to 2 with time quantum 2. If we run P1 from 0 to 2, then burst time reduced from 5 to 3. Now check if P1 got completed. No, P1 is not complete yet. We are at point 2 now. Check which process are ready at point 2. We see P2 and P3 are both ready. P2 is ready at 1 and P3 is ready at 2. So both processes got ready. Place both processes in the ready queue first according to their arrival time. P2 came first, so we place P2 first, then P3. Meanwhile, we ran P1 from 0 to 2. After 2, CPU will preempt and bring another process. This is context switching. Save the running process and bring a new one. We save the context of the running process. Context means PCB, process control block, which contains all information of that process. We save context so when the process comes again in future, we don't have to run it from 0. We bring P2 here and check. P1 ran from 0 to 2. When P1 goes to ready queue, it will come behind P3. When context switching was happening, we saved P1's value, and at that time P2 and P3 came in ready queue. Now we take out P2 and run it for time quantum 2. This value becomes 2. Now check which processes are ready at 4. P4 also got ready. Now place P4 in ready queue first. Then check if P2 is left or not. Yes, P2 is still left. Still 2 left. So place P2 in the ready queue after P4. We bring P3 here for 2 time quantum. So the value becomes 6, but P3 gets completed because its burst time was 2 and we ran it up to 2. Now check at 6 if there is any new process ready or not. All processes already came in the ready queue. Check if P3 is still left or not. P3 is already completed and terminated. Take out P1 from ready queue. When we execute P1 for 2 time quantum from 6 to 8, burst time reduced from 3 to 1. Now check if some new process came at 8 or not. No new process come. Check if P1 is still left or not. Yes, P1 is still left. So place P1 in the ready queue. Next, take out P4 and place in the running queue for 2 time quantum, but P4 needs only 1 time unit, so we ran 8 to 9. So P4 get executed and terminated. At 9, you can bring the next process. Next process is P2. We run P2 for 2 time units, so it becomes 11 and P2 completes. Then we have P1. We run P1 up to 12 because it has just 1 time left. Now all processes get complete at 12. This ready queue sequence is very important. If this sequence gets even slightly changed, changed, your answer will be wrong. You can't remember this sequence without making ready queue. From the Gantt chart, check complete times. P1 completes at 12, P2 at 11, P3 at 6, P4 at 9. Now turnaround time is completion time minus arrival time. So it will be 12 minus 0, 12, 11 minus 1, 10, 6 minus 2, 4, 9 minus 4, 5. So P1 12, P2 10, P3 4 and P4 5. Now waiting time is what? Waiting time is turnaround time minus burst time. So 12 minus 5, 7, 10 minus 4, 6, 4 minus 2, 2 and 5 minus 1 equal to 4. For response time is equal to CPU first time when it came first to the CPU minus arrival time. So P1 got CPU first at 0, arrived at 0. So 0 minus 0 equal to 0. P2 got CPU first at 2, arrived at 1. So 2 minus 1 equal to 1. P3 got CPU first at 4, arrived at 2. So 4 minus 2 is 2. And P4 got CPU first at 8, arrived at 4. So 8 minus 4, 4. Now that is whole concept of round robin scheduling. This is very important scheduling and you can practice even more question on this. Now we are moving forward to priority scheduling with preemption. Now let's see a numerical on priority scheduling with preemption mode. Here we have 4 processes with their arrival time and burst time. The criteria in priority scheduling is priority. The process with higher priority gets CPU first. First, find out what priority means in the question. Higher the number, higher the priority, or lower the number, higher the priority. Most of the time it's mentioned in the question. Here we have given that the higher is the number, the higher is the priority. So 40 has the most priority. Using Gantt chart, start from 0. Check which process has arrived at 0. If only one process arrived, there is no criteria needed. If 2 or more processes arrive, then use the criteria. At 0, only P1 has arrived. So we shift P1 from ready queue to running queue. In preemptive mode, we have to be very careful. In non-preemptive, if you have P1, it will execute completely. But in preemptive, run it only up to one time unit. Run P1 from 0 to 1. So burst time reduced from 5 to 4. At time 1, check which processes are in the ready queue. P1 is already there and P2 also arrived at 1. If we have 2 processes, there is a competition. So we use priority criteria here. P2 has more priority. 20 is greater than 10. So preempt P1. P1 goes back to the ready queue and P2 moves to the running queue. We save P1's context that it ran up to one time period. Now run P2 from 1 to 2. Now burst time reduced from 4 to 3. At point 2, P3 also arrives. Check priority among P1, P2, P3. P3 has highest priority. So preempt P2. P2 goes to the ready queue and P3 gets executed from 2 to 3, reducing burst time from 2 to 1. At time 3, check which process arrived. So P4 arrives at 4. So on 3, same process as before. P3 still has highest priority. So run P3 again from 3 to 4 and it gets terminated. Burst time becomes 0. At time 4, P4 arrives with priority 40 greater than P1 and P2. Execute P4 from 4 to 5 and it gets terminated. Burst time was 1. At 5, P2 has more priority than P1, so execute P2. Since all processes have arrived and P2's priority will always be greater than P1, you can run P2 continuously from 5 to 8, 3 times unit left and terminate it. Now only P1 is left, so run P1 from 8 to 12, 4 time units are left and complete it. From Gantt chart, completion means P1 at 12, P2 at 8, P3 at 4, P4 at 5. So this is the completion time. And what is turnaround time? Turnaround time is completion time minus arrival time. So 12 minus 0 equal to 12, 8 minus 1 equal to 7, 4 minus 2 equal to 2, 5 minus 4 equal to 1. Now what is waiting time for that? Turnaround time minus burst time. So 12 minus 5 equal to 7, 7 minus 4 equal to 3, 2 minus 2 equal to 0, 1 minus 1 equal to 0. If two processes have same priority and same arrival time, then work as first come first serve. If everything is same, execute according to process IDs. So this is the whole concept of what? This is the whole concept of priority scheduling in with preemption. Now moving forward to process scheduling with input output operation. Let's solve a question where each process uses CPU, then shift to input output device, then again comes back to CPU. We have 4 processes with arrival time, priority and burst time given. In this question, each process will use CPU for some time, then shift to input output device, then each process has its own input output device, then again come back to the CPU. The mode is priority based and preemptive. Here lower the number, highest the priority. P1 has highest priority, then P2, then P3, then finally P4 has the lowest priority. At time 0, only P1 arrives. Run P1 up to 1 unit. Always run one by one in the preemptive mode to avoid missing highest priority processes. P1's CPU time completes and it start input output work for 5 time units. Now at time 1, Check which process arrived. No one. So CPU stayed idle for 1 to 2. Now at time 2, P2 arrives. Run P2 up to 1 time unit, 2 to 3, reducing CPU from 3 to 2. Now at time 3, P3 and P4 arrive. P2 is in the ready queue. Among all, P3 has the highest priority. So run P3 from 3 to 4, reducing CPU from 2 to 1. Now at time 4, P3 still has highest priority. So run P3 from 4 to 5. Completing its CPU becomes 0. Now P3 start input output for 3 time units. At time 5, run P1 from 5 to 6. P1's input output completes. Okay, so P1 comes back to the ready queue. Among P1, P2, P4, P1 has the highest priority. So continue P1 from 6 to 7. At time 7, P1 continues from 7 to 8. Now at time 8, P3's IO also completes. So P3 comes back. Now P3 has highest priority among remaining processes. Run P3 from 8 to 9, completing its remaining CPU. P3 exists. At time 10, run P2 from 10 to 11, completing its CPU. P2 start IO for 3 time units. At time 11, only P4 left in the queue. Run P4 from 11 to 12, reducing CPU from 2 to 1. At time 12, run P4 from 12 to 13, completing its CPU. P4 starts IO operation now. Therefore 4 time units. Now at time 13, CPU stays idle because both P2 and P4 are doing IO operation. At time 14, P2's IO operation completes. Now P2 comes back and complete at 15. So at time 17, P4's IO operation completes. So P4 comes back and completes at 18. Completion time means P2 at 15, P3 at 9 and P4 at 18. These are the completion time of all the processes. Remember to solve these questions carefully because they involve numericals. Now moving forward to multi-level queue scheduling. The topic is multi-level queue scheduling. All the scheduling algorithm we saw until now, we just take only one ready queue there. All the processes that we have to execute, we put all of them in the ready queue. And in ready queue, out of all the processes, we extract some processes and give them to CPU. We pick some processes on the basis of scheduling algorithm and execute it on the CPU. But what is the multi-level queue scheduling concept? In the real life, we don't have the just one type of process. Process can be different types. Multi-level queue says that there are 3 types of processes. First, system processes which have highest priority. System processes are like interrupts. If an interrupt generates in the system, then all the work will be stopped and first the operating system will handle the interrupt. Second, interactive processes which have medium priority. Interactive processes means like if you are watching a movie on VLC or interacting with an application directly, that's called the interactive process. The third one is batch process. Batch process has the lowest priority. They are also called background processes where we give multiple processes to the system and system keeps executing them in the background. So if I have these different type of processes which have different priorities also, then why should there be only one queue for all of them? What multi-level queue says is that there must be different queues for every process type. Each one will have its own ready queue. When a system process comes, we will place it in the system queue. When there is an interactive process, we will place it in the interactive queue. If there are batch processes, we will place them in the batch queue. And we have already decided the priorities. System processes get highest priority, interactive processes get medium priority, and batch processes get lowest priority. The second important point here is that every queue can have its own algorithm also. If a process is a system process, it might use round robin scheduling algorithm. If I have 5 to 10 interactive processes, then how to execute them? We might use shortest job first. These scheduling algorithm can be same or different for different queues. So the biggest advantage here is that we are categorizing the process according to their different real life scenarios and giving them appropriate treatment. But there is a problem. Obviously, if you keep getting too many system processes, then there will be no turn for interactive and batch processes. Then they will run like late on the CPU. Whenever system processes come, they will get executed first, and batch and interactive process will keep waiting. So there will be a problem of starvation because the process with the lower priority will keep waiting for their turn. Now to remove this problem, we can use multi-level feedback queue, which is the next version of multi-level queue. Now moving forward to multi-level feedback queue scheduling. The topic is multi-level feedback queue. We have seen a problem, starvation. The problem occurs because when higher priority process like system processes keep coming, the lowest priority process will keep waiting for their turn. When their turn is about to come, another system process comes and again they have to wait. So the method to remove the starvation problem is feedback. The lowest priority process give their feedback and we keep upgrading them gradually. I have taken a simple example here. If I have an P1 process process, a batch process of lower priority, and let's say its execution time is 19 time units. How will it proceed? First, since it's a batch process, it will go in the lowest priority queue. It can it can't go in any other queue initially. When it comes to this queue, let's say it needs a 19 time unit to complete, but it will get 19 time unit only when it gets its turn first. So what we do here, it run it up to 2 time quantum. Out of 19, we ran it up to 2 time quantum. Then 17 is left. We give it feedback. We send it to the next higher queue. P1 doesn't have to wait much longer. Its turn will come in the this queue, second queue, and it runs for 4 time quantum in this queue. So if it runs for 4 quantum, then how much is left? It's 13 time units left. After this, because of other process will also come in this queue, so we won't keep this in the same queue for too long. We keep shifting it, keep giving it feedback. So we send it to the next queue. So now if it turns for 8 time units in this queue, then how much is left? It's 5 time units. It needs 5 more time unit to get fully executed. So we send it again to the next queue. In this final queue, we can use first come first serve, or leftover 5 time units get executed using first come first serve in the final queue. So we are taking care of both things. First, lowest priority process should not be face the starvation. We keep changing their queue level. If the queue keeps changing, then their turn will keep come faster. Second, if there are high priority processes, they don't have any problem. They will keep running as they always do. That's why we use multi-level feedback queue, just to remove the starvation which occurs in multi-level queue scheduling. So that was the whole concept of CPU scheduling algorithms and multi-level queues, and this is the very important topic, and you have to prepare accordingly. So that's it for this video. We will meet in next video. Until then, bye bye.